You ever notice how some things in life happen in a flash while others seem to take forever? Think about it, a lightning strike versus a mountain slowly wearing away. Well, guess what? The world of chemistry is exactly the same. Chemical reactions have their own speed limits, from ridiculously fast to painfully slow. So what's actually setting that speed? Let's get into it.
To really get to the bottom of this, let's start with a little puzzle. Imagine you've got wood, but in two totally different forms. A big, solid log can smolder all night, releasing its energy super slowly. But if you take that exact same wood and you grind it down into a fine powder, sawdust, it can burn so fast that it literally explodes. It's the same stuff, so what's going on there?
And this isn't just about wood. Not at all. You see these kinds of contrasts everywhere. A car slowly rusting away over years? That's a chemical reaction. A firework exploding in a brilliant split-second flash? Also a chemical reaction. Food going bad in your fridge is chemistry, just like that crazy violent fizz you get when you drop pure sodium into water. There have to be some hidden rules here, right? What is governing all this speed?
All right, so to solve this whole thing, we're going to look at 5 key factors that basically act like control knobs for chemical reactions. The first one, and you could argue it's the most basic, is just the nature of the stuff you're working with.
Okay, check out these two metals. If you leave a chunk of iron outside overnight, it's pretty much fine. It's the tortoise in this race for sure. But sodium? Whoa, sodium is the hair. It is so reactive that it will tarnish and react completely with the air in that same amount of time. It's just baked into their chemical DNA. Some substances are naturally lazy and others are just born ready to go.
But it's not just what the material is, it's also about the shape it's in. And this brings us to our second big factor, the physical state of what we call the reactants. That's just a fancy word for the ingredients in a reaction.
Okay, here is the absolute key idea for this whole section. For a chemical reaction to happen, the molecules have to physically touch each other. Think of it like a handshake. They've got to get close enough to interact. If there's no contact, there is no reaction. It really is that simple. And as you're about to see, the amount of space available for that handshake changes everything.
So imagine a single, solid lump of something. The reaction can only happen on its outside surface, right? But what if you smash it up? Boom! You've instantly created all these new surfaces where reactions can start. Now grind that down into a fine powder, and you've just created a gigantic number of contact points. More surface area means more places for the reaction to happen all at the same time.
And that brings us right back to our original mystery. The log has a small surface area for its total size, so it just burns slowly from the outside in. Smaller pieces of wood have way more surface area, so they burn faster. And the sawdust, it has an absolutely enormous surface area, which lets it react with oxygen so fast that it goes kaboom. It was all about how many handshakes could happen at once.
Okay, so we've covered what the reactants are and what shape they're in, but the story doesn't stop there. We also have to think about the environment around them. Let's look at two huge ones, temperature and concentration.
We all know this one from our own kitchens, right? Food spoils way faster on the counter than it does in the fridge. Why? Because the cold temperature inside the refrigerator is slowing down all those little chemical reactions that make food go bad. When you heat things up, the molecules get more energy. They start zipping around faster, bumping into each other more often and with more force, which means more successful reactions.
And get this, here's a really handy rule of thumb. For a lot of common reactions, just raising the temperature by 10 degrees Celsius, that's about 18 degrees Fahrenheit, can actually double the speed of the reaction. It's a surprisingly powerful effect for what seems like a small change. All right, now let's talk about concentration. This is basically about how crowded the molecules are. In the air we're breathing right now, only about 20%, or 1/5 of it, is the oxygen that's needed for burning. The other 80% is mostly nitrogen, which just kind of gets in the way. So for something to burn, the fuel has to find that 1 in 5 oxygen molecule. So, for example, phosphorus burns pretty quickly in normal air. But what happens if we crank up the oxygen concentration? Imagine putting it in a container filled with 100% pure oxygen. Well, now every time it bumps into a gas molecule, it's a useful one. The reaction rate just goes through the roof. The more reactants you pack into the same space, the more they'll collide, and the faster the whole thing goes.
So we have talked about the reactants themselves and their environment. But there's one more factor, a kind of secret ingredient that acts like a chemical shortcut. Let's talk about catalysts.
So what is a catalyst? It's a substance that makes it easier for a reaction to happen. It basically provides a different, easier path for the molecules to take. The coolest part is that it helps the reaction along, but it doesn't get used up in the process. It's kind of like a chemical matchmaker.
It introduces two molecules, helps them get together, and then just steps away, totally unchanged, ready to do it again.
Here's the perfect example. You probably have a bottle of hydrogen peroxide in your bathroom cabinet. Right now, it's decomposing. It's breaking down into plain old water and oxygen gas. But this process is incredibly, incredibly slow. If you just leave it alone, it could take months, even years.
So that leads to a great question. If it's so slow, why does it foam up and fizz like crazy the second you pour it on a little cut? That super slow reaction suddenly becomes almost instant. What changed?
And here's the answer. Your own body, specifically your blood and tissues, contains a natural enzyme called catalase. This enzyme is a ridiculously good catalyst for breaking down hydrogen peroxide. It provides that super easy shortcut we were talking about, which causes the reaction to speed up dramatically, releasing all that oxygen gas at once. And that is the foam that you see.
So there you have it. We've kind of pulled back the curtain on how chemical reactions get their speed limits. You see, it isn't random at all. It's a set of predictable rules and levers that scientists and even our own bodies use all the time to control the world on a molecular level. So just to recap, these are the 5 main levers you can pull to control the speed of chemistry. First, the basic nature of the substances themselves. Second, their physical state, especially surface area. Then you've got temperature and concentration. And finally, you have the secret weapon, adding a catalyst.
The big takeaway here is that we are constantly messing with these 5 factors, whether we realize it or not, from cooking food faster in a pressure cooker to slowing down rust with a coat of paint. So the final question I have for you is, now that you know the rules of the game, where else can you see them in action? What parts of your world are secretly being controlled by these fundamental principles of chemistry?